See, the diameter of the impeller of a centrifugal compressor is 2, so the diameter ratio that is, and the pressure ratio is 4. At a speed of 1200 rpm, the flow rate is 10 meter cube per second of free air. The isentropic efficiency of the compressor is 84%. The blades are radial at the outlet and entry is radial at the inlet. The velocity of flow remains constant at 60 meters per second through the impeller. Calculate the power input to the machine, the impeller diameters at the inlet and outlet, and the blade angles at the inlet. The suction is from the atmosphere at 100 kilopascals and 300 Kelvin. So let us try to data what is given, then we'll try to solve this problem. So data what is given. So they are given the ratio, that is outer diameter to inner diameter as 2. At the same time, they are given the pressure ratio as 4, and they are given the speed as 12,000 rpm, and the discharge is 10 meter cube per second. The total to total efficiency or compressor efficiency is around 84%, and it is radial at the exit. That means the beta 2 is 90 degrees. The condition is beta 2 is 90 degrees, and it is radial at the inlet. That means my alpha 1 is 90 degrees. That is the meaning of it. And they are telling that my VF1 and VF2 remain same as 60 meters per second. The atmosphere, the suction is from the atmospheric at 100 kilopascals and 3T, that is your, so both are absolute actually. So it is P01 is 100 kilopascals and T01 is around 300 Kelvin. So this being air compressor, I can take gamma as around 1.4. What we are supposed to find? Okay, the power input to the machine, that is the first one. It is the power input P. The second one, the diameters D1 and D2. And the third one is the inlet blade angle, that is at the beta 1. Okay. Now here, before I proceed with the solution, I need to draw the velocity triangle as well as the HS or TS diagram. So both I need it. So what I'm going to do, to the right hand side, I'm going to draw the HS diagram. Okay. Then to the left hand side, I'm going to draw the velocity triangle. So this is my HS diagram or TS diagram, doesn't matter. So HS or TS doesn't matter, so it remains the same if you represent in terms of temperature or in terms of your enthalpy. Okay, these are my pressure lines. It will be going something like this. Okay, now this being a compressor, so if I go by isentropically, it will go like this. So this is from 0, 1 to 0, 1 isentropic. I call it as 0, 1 dash or 0, 2 dash. This is 0, 1 to 2. Okay, this is 0, 1 to 0, 2 dash. And if I go according to the actual process, the compression will be something like this. So it will go to 0, 2. This is my P01. This is my P02. This is how this particular thing happens. So at any given point, this will give my T02 or H02. This H02 dash, this will give my T02 or H02. This will give my T01 or H01. So these are isentropic HS enthalpy diagram or TS diagram. So correspondingly, now let us try to write the velocity triangle. So this being a compressor, so I need to have an outer diameter and I need to have an inner diameter. So this is my, we call it as tip diameter, and I do have the hub diameter. So let us draw your blade actually. So the blade is something like this. Okay, this is radial exactly. Okay, and usually it will be rotating in this direction. So I told that your fluid, see, whatever this particular thing, no, your fluid is pushed by your blade. So this being a radial exit, okay, at the exit, my velocity triangle will look something like this. It is a simple straight line, okay, it's a simple straight line, something like this. So this will be my beta 2, okay, this will be my alpha 2, this is my V2, so this is my VR2, which is also equal to VF2, and this will be my VW2, which is also equal to U2, because for a radial exit. So why this particular thing? Because this is beta 2, which is exactly radial. That means it's exit at the 90 degrees. Now similarly, if I try to draw the inlet velocity triangle, okay, my inlet velocity triangle will be something like this. See, this is my alpha 1, okay, and I do have your relative velocity will be something like this, okay. So okay, this is my triangle, okay, this will be my VR1, okay, this will be the angle that is making beta 1, this is my alpha, which is exactly radial, and this is my V equal to VF1, so this is my U1. So for this condition, my VW1 is equal to 0. What is mean by it actually? No whirl at the inlet. This particular kind of a problem. So I have drawn the velocity triangle and I have drawn the HS diagram. Now let us try to solve one by one. See now, if you consider what is data that is given, so they given the pressure ratio. See, let's try to look at the isentropic process HS diagram. See, from the HS diagram, from the HS or PS diagram. Okay. So see, in the one they are given pressure ratio. What is pressure ratio? It is the outlet pressure by inlet pressure. They are given it as 2. It was a numerical. Sorry, 4. This pressure ratio is 4. Diameter ratio is 2. So it is 4. Now, for an isentropic process, we know that what is the formula? It is T2 by T1 is equal to P whole to the power of gamma by gamma minus 1. This we know actually. Now here the temperatures are in absolute, the pressures also will be absolute. So for this condition, for the process along the blue line 0,1 to 0,2 dash, I can write it as, see, T02 dash by T01 is equal to P02 by P01 whole to the power of gamma minus 1 by gamma. So now P01 is 300, P02 by P02 is 4. So let's substitute everything. So I can get the T02 dash. So T02 dash is equal to your T01 into your pressure ratio to the power of gamma by gamma minus 1 by gamma. So if I substitute the values, it is T02 dash is equal to 300 into 4 to the power of 1.4 minus 1 by 1.4. So my T02 dash is equal to, if I substitute in my calculator, I am getting around 445.8 Kelvin. Okay, I am getting a value of 445.8. This is the temperature that. Now, they have given the compressor efficiency. See, the compressor efficiency are total efficiency. The compressor efficiency is given by, what is it actually? The compressor efficiency is nothing but your actual work done to your IDC. You have the isentropic work done to your actual work done because it's a compressor. So if you look at what is my isentropic work done, Cp into T02 dash minus T01 divided by Cp into T02 minus T01. Okay, so let me write that. So this is nothing but your isentropic work divided by actual work. Okay, let me if I substitute in terms of temperatures, it will be Cp into T02 dash minus T01 divided by Cp into T02 minus T01. So Cp just simply cancel off. I am left with my compressor efficiency is equal to, I am getting in terms of only temperatures, that is T02 dash minus T01 divided by T02 minus T01. So here I know the compressor efficiency is given as 84%, T02 dash as 440.8 calculated, and T01 is 300 Kelvin, which is given in numerical. I can find the actual temperature, which is T02. So let's substitute and find the T02. Okay. Now 0.84 is equal to 445.8 minus 300 divided by T02 minus 300. If I do the cross multiplication, T01 into 300.84 to the right hand side, 445.8 minus 300, I am getting 145.8. Okay, if I do all those things in my calculator, I am getting my T02 as 473.6 Kelvin. Now, whether my calculation, what I have done, is correct or not, I need to check. Okay. Now, what is the value of T02 dash I got? It is 445.8. And T02, I am getting it as 43.6. So this number should always be greater than your T02 dash. Why? You can look into your TS diagram or HS diagram. My T02 is greater than your T02 dash. How you can? This is how I got the temperature. Now let us find the work done, actual work. Okay. So work done is given by actual work done is given by Cp into T02 minus T01. Okay. So actual work done, W is equal to W actual is equal to Cp into T02 minus T01. So this being an air, for air, Cp I can take it as 1.005 kilojoules per kg degree Kelvin. I can make an assumption. So let us substitute it actually. So I am going to get 1.005. So T02 is, just now we calculated, is 473.6 minus T01 is 300. If I put into my calculator, see here, you have to be very careful. See, your Cp substitute in terms of kilojoules. My W, what I am going to get, will be in kilojoules. So W actual is equal to, I am getting it as 174.46 kilojoules per kg. Why this particular thing actually? Because I am trying to substitute the value of your, so the mass flow rate is 1. So if that is the case, my actual work done is actually, it is your specific work actually. Okay, it is my specific work. Now, also we know that, see, for beta 2 is equal to 90 degrees. Okay, we have from Euler equation. From Euler equation, we have studied from the Euler equation, for VW1 is equal to 0. We know that W axis is also equal to VW2 into U2. Okay, here VW2 is equal to U2. Either I can put VW2 square or V2 square. So what will happen? W actual will be equal to either VW2 square or U2 square. Okay. Now let us try to find U2 square. Okay. Now if I want to substitute, so W actual is 174.46. I got it. So if I substitute W actual equal to U2 square, so here W actual is 174.46 46 kilo, that is into 10 to the power of 3 is equal to your U2 square. So what will be my U2? U2 is equal to square root of 174.46 into 10 to the power of 3. If I put into my calculator, I am getting it as U2 is equal to 417.7 meters per second. Okay. Now, this is the value of your exit, or we call it as outer peripheral velocity, that is U2. Okay, U2 is equal to 417.7. Now, what I need to find actually, I need to find power. I need to find my diameters, all those things. So, if I want to find, see, what I have found is specific work. See, what I have here is specific work. Specific work multiplied by mass flow rate, I'll be getting the power. Okay. Now I don't know the mass flow rate. Given the values, I should be able to find mass flow rate. What is mass flow rate actually? It is your density. See, mass flow rate is given by. So the mass flow rate is given by this particular formula. So what is the formula? Mass flow rate. Mass flow rate is given by m dot is equal to rho into A into V, where V is the velocity, or what is your A into V? It is your discharge, rho into Q. Okay. But Q is given as 10 meter cube per second. So what will be the value of density? I need to find it. So now, for a pressure, see, if you have something like a table, if you have a table which gives the properties of the air, I can use the table and get it. Otherwise, at 100 kilopascals of pressure, if you get into this thing, for 100 kilopascals, my density from the table I am getting it as around 1.18 kg per meter cube. If you have a table, you can use the table and you can get the value. Or if you don't have any table, if you can use 1.2 kg per meter cube. Okay. So 1.18 is roughly the number which you are going to get it from the tables. Or you can use 1.2 kg per meter cube for solving the problem. Now if I substitute this rho over here, what I am going to get actually, what will be my mass flow rate? Mass flow rate is equal to 1.18 into your discharge is 10. I am getting around 11.8 kg per second is the mass flow rate. Now what I need to find? I need to find the power. Okay. The first thing is the power developed, the power required. Okay. So what it is actually, that is P is equal to mass flow rate into your specific work, whatever the actual work, which is 174.46 kilojoules per kg. So if I substitute over here, I am getting 11.8 into 174.46 kilojoules per kg. So if I multiply, I am getting my power as 2050 kilowatts. Or if you want to convert it to megawatts, it will be roughly 2 megawatts, 2.05 megawatts. Okay, so the first thing I got it. Now the second thing I am supposed to find is your diameter. See, already I know the value of U2. See, what is U2? U2 is your peripheral blade velocity. So U2 is equal to pi d2n by 60. So I have found the value of U2 as 417.7. So in this, I don't know the value of what is unknown. The unknown is my D2. So if I do a simple cross multiplication, D2 is equal to U2 into 60 by pi into n. So if I substitute the values, your D2 is equal to 417.7 into 60 divided by pi into 12,000 RPM. If I substitute, I am getting my D2 as around 0.664 meters or 664 millimeters. See, in the problem what they are given? They are given the diameter ratio, that is D2 by D1 is equal to 2. So therefore, my D1 is equal to D2 by 2. So this will be 0.664 divided by 2, that is 0.332 meters or 332 mm. So I got the values of diameter, that is inside diameter, inner diameter, the hub diameter, or outside diameter, which is called as tip diameter. So once I know this, I can find the, now the last thing I need to find, your blade angle. So the third one what I need to find is actually, it is the inlet blade angle beta 1. Okay, to find that, let us come to inlet velocity triangle. Okay, if you look at the inlet velocity triangle, what is tan beta 1? So tan beta 1 is equal to Vf1 divided by U1. Okay, I don't know the value of U1, but I can find U1. So U1 is equal to pi D1 n by 60. Because D1 I know, n I know, I can substitute, I can find the value of U1. So Vf is given in the numerical as 60 meters per second. If I substitute, take tan inverse of it, I will get the value of beta 1. Fine. So to find the beta 1, so let me write that. To find the inlet blade angle beta 1 from the inlet velocity triangle, tan beta 1 is equal to Vf1 divided by U1. Okay. Now I don't know the value of U1. So U1 is equal to pi D1 n by 60. Let me substitute. So pi into 0.332 into 12,000 divided by 60. So I am getting around 208.6 meters per second. Okay. So now I got the value of U1 also. Now let me substitute it. So tan beta 1 is equal to Vf1 is equal to Vf2 is equal to Vf, that is 60 meters per second, which is given in the numerical. 60 divided by 208.6. So if I substitute, if I take the tan inverse of that is tan inverse of 60 by 208.6, I am getting my beta 1 as 16 degrees. So all the things which were supposed to be found from the in the numerical are found. So the first one was power, which was 2050 kilowatts. The second one was outer diameter, which is 0.664 meters, and the third one is my inner diameter, which is 0.332 meters, and the last one is my inlet blade angle, which is 16 degrees. Okay, so everything we found. So what is the first thing you have to do actually? Read the problem statement, go step by step and try to solve it. Now, if you try to look into the second problem is very similar to your first problem. Okay, little bit of variations are there. But where your exit velocity triangle, your beta 2 is less than 90. Okay, there the beta 2 is less than 90. So you try to solve that problem because the outlet blade angle, see, look at this, the outlet blade angle, this is the second problem. I want you people to try this problem. Okay, the impeller of a centrifugal compressor has the inlet and outlet diameters of 0.3 and 0.6 respectively. The intake is from atmosphere at 100 kilopascals and 300 Kelvin without any whirl component. That means my VW1 is equal to 0. The outlet blade angle is 75 degrees. In the first problem what I solved, it was 90 degrees. Now it is 75 degrees. The speed is 10,000 rpm and the velocity of the flow is 120 meters per second. If the blade width of the intake is 60 mm, calculate the specific work, exit pressure, mass flow rate, the power required to drive the compressor is the overall efficiency assumed to be around 70%. It's very, very similar to your first problem. Little bit, one other thing is actually where they are given the width actually. So they have given the width actually. So in that case, I need to find the discharge. So where discharge is given by your area, flow area into velocity of the flow. That's the only thing. So what is it actually? The only major difference from first problem to this problem is Q is given by pi d1 b1 into vf1 is equal to pi d2 b2 into vf2, where this is your area of flow at the inlet, this is your area of the flow at the exit. So this is the only change which you people, from where you have to find. In the previous problem, Q was given, here you have to find the Q. So once you know the value of D1, you know your B1 is given, just substitute that, find the value of your discharge and try to solve it. It's very similar to your previous problem. In the previous problem, pressure ratio was given, here you are supposed to find the exit pressure. So it's very similar to your first problem. I want you people to try this problem, second problem. What are you doing is, I'll try to solve the third problem. Okay, the third problem I'll try to solve. Okay. A centrifugal compressor runs at 15,000 RPM and produces a stagnation pressure of 4, stagnation pressure ratio of 4 between the impeller inlet and outlet. The stagnation conditions of air at the intake are 100 kilopascals and 300 Kelvin. The absolute velocity of the compressor intake is without any whirl component. At the exit of the impeller, the flow component of velocity is 135 meters per second. The blades are radial. Okay. The total to total efficiency of the compressor, that is the compressor efficiency is around 78%. Draw the velocity triangles and find the blade angle at the inlet. Okay, it's very similar to the first problem. The extra thing what we are trying to do is actually also compute the slip and slip coefficient. Take exit rotor diameter as 0.58 and inlet rotor diameter as 0.25. So this is what they given in the numerical. So we'll try to solve this. Okay, let's try to write the data what is given. Solution, the data that is given. So they given speed as 15,000 RPM. Okay, speed as 15,000 RPM. So let me write that N is equal to 15,000 RPM. Okay, the pressure ratio, that is P02 by P01 is equal to 4, and the inlet pressure, stagnation pressure is 100 kilopascals. The inlet stagnation temperature is 300 Kelvin. The inlet whirl velocity is absent. That is, there is no whirl at the inlet, so VW1 is equal to 0. My flow component at the exit VF2, it is 135 meters per second. Okay, and they are given the total to total efficiency or compressor efficiency as 78%. It is 0.78, and they are given the outlet diameter which is 0.58 meter. They are given the inlet diameter which is 0.25 meters, and the blades are radial at the exit, that is my beta2 is 90 degrees. So I have written all the data that is given. So what we are supposed to find? Okay, the first one is I need to find my blade angle, that is beta1, inlet blade angle, and the second thing is slip and slip coefficient. So here also let me try to draw your velocity triangle. So the velocity triangle is very similar to what I drew for the first problem, and even I need to draw the HS diagram or PS diagram also. Let me draw it again. So your PS diagram looks something like this. So I have my temperature, entropy. So the pressure curves would be going something like this. They are not parallel, but they are divergent. So this is my compression from 0,1 to 0,2 dash, and your actual compression will be something like this. It is from 0, 1 to 0, 2. So this is my P01. This is my P02. Okay. This is my HS diagram. So similarly, if I try to draw the velocity triangle, so this is my hub diameter, this is my tip diameter, and I do have my blade will be something like this. And if I try to draw your exit velocity triangle or inlet velocity triangle, it will be something like this. Okay, let me draw this. Okay, let me draw the inlet velocity triangle. Okay, this is my inlet velocity triangle. So this is my your beta 1. So VR1. This is my V1, which is also equal to VF1 because my VW1 is equal to 0. This is my alpha 1. This is my U1 because it is rotating in clockwise direction because this is a compressor. Okay. Now exit velocity triangle. I need to draw this. So if I try to draw the exit velocity triangle, it will be something like this. This is what I am trying to draw in the dark. So this is my simple right angle triangle what I am going to get. Okay, so this is my velocity triangle. This is my beta 2, which is radial. So this is my VW2, which is also equal to U2. Okay, this is my alpha 2. This is my VR2, which is also equal to your VF2 and your V2. I got all my velocity triangles. So now, if there is a slip, what will happen? If there is a slip, what I am going to get actually, I am going to get my VW2 dash, I call it as, which is axial, which will be less than your VW2. So what will happen here actually? My VW2 will become smaller. So if I try to overdraw here, somewhere here, so I am going to get my VW2 dash somewhere here. I am going to get VW2 dash. So because of this VW2 dash, what will happen to your see? Your U2 will remain the same. So if I try to extend this actually, my velocity triangle will become something like this. So beta 2 dash, so beta 2 dash, okay, I am going to get a beta 2 dash, which will be less than your beta if there is a slip. So because of the slope, I am going to, what is going to happen? See, this is what is going to happen. So there is some kind of a push. So VW2 dash will become smaller. That means the work requirement will become smaller. And beta 2, it was supposed to be radial, will become smaller. So I am going to get a beta 2, that is my exit blade angle, which will be acute if there is a slip. Okay, this is what my velocity triangle will look like. Now let us try to compute whatever is possible from the what is data that is given. So from the HS diagram, okay, from the HS or TS diagram, what we have my T02 dash, very similar to the previous problem. T02 dash by T1 is equal to your pressure ratio or P02 by P01. So P02 by P01 whole to the power of gamma by gamma, because this is from the same formula. T2 by T1 is equal to P2 by P1 whole to the power of gamma minus 1 by gamma. So the unknown is T02 dash. So let me find that. T02 dash is equal to P01 into P02 by P01 whole to the power of gamma minus 1 by gamma. So here also gamma is equal to 1.4 because this is an air. So let me substitute that and you can find it T02 dash. So T02 dash is equal to T01, they are given it as 300 into your P02 by P01 is 4, 1.4 minus 1 by 1.4. Already we have found it is T02 dash is equal to 445.8 Kelvin. So once again, what is my compressor? So what is the compressor efficiency? So the compressor efficiency is given by your isentropic work, that is Cp into T02 dash minus T01 divided by Cp into T02 minus T01. Or I am going to get in terms of temperature as T02 dash minus T01 divided by T02 minus T01. Now, if I try to substitute the values, what is the compressor efficiency? It is 0.78 is equal to 445.8 minus 300 divided by P02 minus 300. I will end up with my P02 as 486.92 Kelvin, okay, which is greater than your T02 dash, which is very similar to what we got in the first problem. Okay, now they have given the diameters. Okay, they are given the diameters D1 and D2. They are given the speed as 15,000 RPM. So let us try to find the peripheral velocities. Okay, so peripheral velocities or blade velocities. Peripheral velocities. U1 is equal to pi D1 N by 60, which is equal to pi into D1 is 0.25 meters into 15,000 RPM divided by 60. I am getting around 196.35 meters per second. So what is my U2? U2 is equal to pi D2 N by 60. So my D2 is around 0.58 meters. So 0.58 into 15,000 divided by 60, I am getting around 455.5 meters per second. So I am able to calculate my U2 as well as U1. Now let us go to the inlet velocity triangle. Fine. Let us go to the inlet velocity triangle. So from the, what is my tan beta 1 here? I need to find the angle beta 1. So tan beta 1 is equal to Vf1 divided by U1. Okay. So Vf1 is how much? 135, which is given in the problem. So U1 just now we found around 196.35. If I substitute take tan inverse of it, I am going to get my tan beta. Okay. Now let us try to find that. So from the inlet velocity triangle, from the inlet velocity triangle, tan beta 1 is equal to Vf1 divided by U1. So if I try to substitute it, it is actually 135 divided by 196.35. So beta 1 is equal to tan inverse of 135 divided by 196.35. So I am going to get my beta 1 as 34.5 degrees. Okay, so here Vf1 is equal to Vf2 is equal to Vf, which is given in the problem, that is 135 meters per second. It's not changing. Okay. Now what is the exact thing we have to find? The last thing, we have to find the your slip coefficient and slip. Okay. If I want to find that, so what is the first thing I need to do? I need to find the specific work. See, your work actually, what is your actual work? Actual work, the actual work is given by your Cp into T02 minus T01. At the same time, okay, your actual work is equal to Vw2 dash into U dash, so into U2. Vw2 dash into U2, that is my actual work. But ideal work is Vw2 into U2. Okay, so here we have to be very careful. Vw2 dash is actually, it is your actual wall velocity at the exit or at 2. So now if I find the W actual is what actually? W actual is your Cp into T02 minus T01, which already I have found T02 and I know the value of T01 also. I can easily find, therefore, your W actual is equal to Cp is equal to 1.005. Already I know the value of it, so because assumption, and T02 is, I got it as 486.92 92 minus your T01 as 300. So your W actual, I am getting it as around 187.8 kilojoules per kg. Fine. So look at it. Your W actual is VW2 dash into U2. What is my theoretical? It is being a radially exit compressor. It will be either VW square or U2 square. Found U2 square. So already you found U2. U2 is 455.5. Your W ideal is actually, it is U2 square. So 455.5 into square, 5.5 square is actually what is ideal. But actual is VW2 dash into U2. So I am looking at only actual one, so that I need to find this value. So what is your, see here, U2 square or your VW2 square. So what is my VW2? VW2 is 455.5. So if I want to find the slip, actually it is VW2 minus your VW2 dash. So if you want to find this, actually VW2 is equal to your U2. I don't know the value of VW2 dash, which I can find from this actual one. What I want to do, actually, whatever I have done here, I am going to substitute here. Okay, your W actual is equal to VW2 dash into U2. This is 187.8 into 10 to the power of 3 is equal to VW2 dash into 455.5 meters per second. If I do that, I am getting my U2 VW2 dash as 412.4 meters per second. Okay. For a radial exit condition, for the radial exit condition, VW2 is equal to U2, which is equal to 455.5 meters per second. So what is my slip in that case? So my slip sigma is equal to VW2 minus VW2 dash, so which is equal to 455.5 minus 412.4. If I substitute, I am getting my sigma is equal to 43.1 meters per second. So what is the slip coefficient? I can easily find it. So slip coefficient, which is phi, is equal to your slip divided by your ideal VW2. That is VW2 minus VW2 dash divided by VW2. That is 455.5 minus 412.4 divided by 455.5. I am getting my phi is equal to around 0.09. So this, I see whatever is they given in the problem, they asked in the problem, we have found it. Suppose if they ask you to find the power developed, so in that case, what I need to find, actually, I need to find my discharge, I need to find the mass flow rate, then I can find the power also, which is not asked in the problem. In the problem statement, they have not asked this. Okay, if you want, you can find that also. Okay, if you want, you can find that also. If you maybe 2 minutes it will take, so I will add that also. Anyhow, it is not asked in the numerical, so I can do that. So I can find Q is equal to pi D1 V1 VF1. So I have to make an assumption. Only thing is, actually V1 is equal to B2 is equal to some 50 mm or 0.05 meters, something I am making an assumption. This is an assumption, actually, that's it. Anyway, it is not asked in the problem. It is very similar to, because I asked you people to do the second problem. This problem, what I am doing, it may help you there. So pi D1 B1 into VF1 is equal to pi D2 B2 into VF2. So let me substitute and find the discharge. So pi into 0.25 into 0.05 into your VF, they are given it as 135. So I can find my discharge, which is around 5.3 meter cube per second. So what is my mass flow rate? So if I want to find my mass flow rate, it is rho into Q. So rho is equal to, I told that for 100 kilopascals, it is 1.18 kg per meter cube if I take it from the table, or you can simply make an assumption of 1.2 meter cube per kg per meter. So if I substitute, I'm going to get 1.18 into 5.3. My mass flow rate is equal to around 6.34 kg per second. I have found my specific work or actual work. Okay, so which is, if I want to find it actually, either I can go with, see, I have your actual work, which I found it as 180, yeah, 187.8 multiplied by your mass flow rate. So the power P is equal to, your mass flow rate into your actual specific work, which is 187. So if I put it 6.34 into 187.8 kilojoules per kg, if I substitute, I am getting around 1195 kilowatts. So this is the power required to run your compressor. So anyhow, this is not asked in the numerical. I have added this